Now, every Tolkienist knows that you don't mess with the dwarves,
So
right?
it was
Unless you like your knees typed up on
so it was designed as a debugging information format to replace stabs, the much older debugging format. It is a standard. You can find the standard at dwarfstandard.org. It gives all of your source line information, variable types, stack backtraces, etc. If you're interested in debugging information, there's debug info, debug line, etc. That's not what we're interested in. That's just debugging. What's more interesting is debug frame, which describes how to unwind the stack and how to restore registers in the previous call frame. Again, that's for debugging. However, the GCC and other people realized that they also needed some way to unwind the stack for exception handling. And here was the DWARF format that already specified a way to do that. So EH-frame adopts a slightly modified version of the DWARF unwinding format used by debug frame. It's not completely identical to the DWARF specification. It adds pointer encoding. There's some other language. Where the DWARF format allows for language-specific data that can be interpreted as a program likes. And the GCC EH-frame adds some of that. Some of this is standardized. The Linux standard base and the x86-64 ABI discuss some of the additions to DWARF for EH-frame. Some of the changes are just at the whim of the GCC maintainers. Although I should mention that LLVM is binary compatible with GCC in that regard. So it uses the exact same format.
So it was the very devil trying to find information about how this works. Except for an obscure ABI from HP, there is no single document in which these things are presented nicely, and that document is incomplete. So what you have to do is go on the
we'll get that later. So let's look at the actual structure of the EH-frame and debug frame. This is as defined by the DWARF standard. So conceptually, it represents a big, huge table. For every address in the program text, it describes how to set the registers to restore the previous call frame. And you can see a visualization of sort of what that table would look like. I should mention the CFA canonical frame address is a concept that DWARF introduces that can be used when restoring other registers. There is no one standardized thing that it has to correspond to. That's up to the implementation. It's essentially going to be the base of the call frame. So if we look at this table, we notice that it could get sort of large. And there are a lot of rows that are blank, or a lot of rows that are blank, or the exact same thing as the row above them. So this table would be huge. It would be bigger than the whole program. So the DWARF EH-frame, debug frame, is essentially a form of data compression. It's bytecode that describes how to generate this table. So the entire table never needs to be built at once. The entire table is never in memory. Parts of the table are built as needed.
Except the virtual machine that executes this bytecode and produces that table also has the registers of the machine itself mapped into its virtual machine. So we're looking at something that serves a dual purpose and represents much of your CPU in the process.
So for the compression in EH-frame, we've got CIEs and FDEs. CIEs are common information entity. They basically just abstract away some of the information that's shared between FDEs. An FDE is a frame description entity. So you can think of essentially there being one FDE per function. In the case of some optimization, where function code is split into different places and so on, you'll find that there may be more than one FDE per function. There's nothing that requires a one-to-one mapping of FDEs and functions. But essentially, in a simple program, you'll have one FDE for each function. So the FDE for a function describes how, if execution is in that function, how unwinding can proceed to the next call frame, higher up in the stack. So the FDE contains instructions, which are the DWARF bytecode that we're particularly interested in. The rest of it is all bookkeeping details, sizes of pointers and address sizes, and so on. So DWARF is really sort of like an assembly. DWARF expressions are an embedded language in a place where people aren't generally expecting it. And it's a Turing-complete stack machine. So most of the DWARF, there are two types of DWARF instructions. There are DWARF call frame instructions and DWARF expression instructions. As we saw in the table earlier, most of the registers are restored by specifying some offset from the CFA or specifying the register in terms of another register. But the DWARF designers wanted to make a fully flexible system. They weren't designing this for one particular architecture. So they built in a great deal of flexibility. So we have a Turing-complete stack-based machine. Computation works essentially the same way as an RPN calculator, so most of you are familiar with that. But interestingly, it can dereference memory, and it can access values in the registers. There aren't any side effects, which is one challenge, or rather there aren't any side effects as provided by the standard. There are a couple bugs in GCC that can allow you to get some side effects. I'll discuss that later. And current GCC limits computation to 64 stack words, which doesn't seem like a lot until you consider that when was the last time you used a program with 64 local variables? So it's actually quite a bit of space you have to work with. And as I'll show, I wrote a dynamic linker that only used about 20 words on the stack, less than 20 words on the stack. So there's enough space here to do whatever you want.
So again, we're talking about an assembly language and a stack machine that were specifically built to poke around in the processor's memory space and restore registers. So that language is the best you can desire for if what you want to do is resolve symbols, deal with offsets, find elements in data structures. Of course, DWARF debugging format represents your full type information in the debug frames. So you can leverage all of that. This is your ultimate symbol browsing machine, which can, of course, turn into a symbol changing machine.
So let's take a look at some of the DWARF instructions. So these are the basic instructions for specifying the table. We've got set location, advanced location instructions. These don't actually do anything, they just specify which row of the big huge table we're talking about, which text address we're describing the unwinding for. And then we've got instructions for defining the CFA, which is defined in terms of some register and an offset. And then we can define how to restore given registers as offsets from the CFA or in terms of other registers. So this is pretty simple, and there isn't nearly as much that we can do with this. So every register has a DWARF register number. This is all just bookkeeping details. Register mappings are architecture specific. Numbers don't really matter. So within an FTE, rows inherit from instructions above them. So if you advance the location to something and you specify how a register is to be restored when unwinding, and then you advance the location again, the previous register specification still holds for the later text locations until it gets defined as something different.
And as you can see, this is what creates this compression effect for this unwinding table. This is how it's meant to be.
But as I mentioned earlier, the DWARF designers couldn't anticipate what every architecture, every kind of system might need for unwinding. And they wanted to make sure that this format would serve all of them. So one of the DWARF instructions specifies that a register gets restored from an expression. So expressions introduce a different type of instructions. And this is where the Turing-completeness comes in. There's two instructions, expression and val expression. The only difference is that one of them does a dereference. We can use them for essentially the same thing. So expressions have their own instructions. We've got constant values that get pushed on the stack. We've got arithmetic on those values. We also have memory dereference that we can do within these DWARF instructions. We can get the contents of a machine register at the current point in the unwinding. And we have control flow instructions. We've got all your basic comparisons, less than, equal to, etc. We can skip instructions, and we have a conditional branch.
So that's pretty much all you want of an assembly language, right? Being able to reference memory, being able to reference registers, and being able to do conditional jumps.
So returning to the CIE and FTE structure again, we've got an initial location and an address range that determines what FTE applies to. We've got an augmentation, and this is going to become important later. Again, the DWARF standard was trying to be very flexible. So an augmentation allows an implementation to define platform and language specific features. And the return address register is also important because that determines which DWARF register number, which column in the table is used to hold the location that the return address is set. And this doesn't have to correspond to a particular machine register. It's generally column 16 in the table in the x86-64 architecture, which is mostly what I've been working with. So that's sort of a virtual register. It's not an actual hardware register. And then every FTE has instructions. So the information in the EA frame is in some nice text format. This doesn't mean very much. ZPLR is the augmentation string that determines which language-specific augmentations it has. But other than that information doesn't mean much. So for that reason, there have been tools written so people, when working with debuggers and so on, people can understand this DWARF information. readel gives you a human readable view of the same information I just showed in the hex dump. And you can see the CIEs and FTEs and all the DWARF instructions that I'm talking about. Objdump has a function that does essentially the same thing. There's a specialized tool written by David Anderson, DWARFdump, which shows essentially the same thing. But none of these let us modify anything. Actually, David Anderson has been working on a DWARF generation tool, but it's in the very early stages. And when I last looked at his code, there wasn't much there.
So we need an assembler, right? If there is the bytecode, we need an assembler to be able to write programs.
So there's a lack of tools for actually manipulating this DWARF information, which is what we really want to do. So Katana is an ELF modification tool that we developed for a completely different project. It was hot patching research, nothing to do with this. But it had the ELF manipulation framework we needed. Our ELF manipulation was inspired by ELF-SH from the RESI project. And that's a great project for your general purpose ELF manipulation needs. I highly recommend it. It's much more full-featured and mature than Katana is. Or DWARFscript is an assembly language that Katana can create. Here's an example from the Katana shell. We load a program, and then we have a command to create the DWARFscript for it. And DWARFscript was modeled essentially after the sort of output that you get from readel for objdump or DWARFdump. But what Katana can do that these tools can't is that we can load one of these DWARFscript files that we already wrote and then compile it back into the DWARF binary form and put it in a section in our executable.
And then, of course, the exception handling virtual machine will execute it when the time comes, and we manage to trigger an exception.
So here's essentially what DWARFscript looks like. Excuse the horrible formatting on this slide. But you see we're specifying our CIEs, our FTEs, all the instructions for them. So exactly the sort of stuff I've been talking about. So we can modify all of these in plain text. This is just an ASCII file. Modify all of them to do what we want, and then just put it back in the binary. So let's pause for a minute and think about what we can do with this. We can view and modify the unwinding table. We can control the path of unwinding.